So, Schrodinger was able to describe the electron not as a particle, but as a wave. Okay? Now, he got the inspiration from that from a guy named Louis de Broglie. And de Broglie had matter waves. Now, did we talk about the photoelectric effect in here?
Yeah.
Right? And Einstein was able to figure out then that light has a dual nature, that it's a wave, it's electromagnetic radiation, it's got a wavelength and a frequency, we calculated that, but it also, the energy, rather than being smooth, it's in these little tiny packets called photons. Now, a photon is a massless packet of energy, but it has some particle characteristics to it. So light has a dual nature, and that's what Einstein won the Nobel Prize for, is the explanation of the duality of light. The fact that it has a wave nature to it, it has a particle nature to it. Well, Schrodinger said, well, then de Broglie came along, and he did a very simple calculation that said, well, if light can have a dual nature, then maybe that matter can have a dual nature. And so he derived an equation. It's on the bottom of page 3 where it talks about matter waves in your notes. Most of everything on page 1 and 2 just kind of we talked about in the video as we went along. But it's the wavelength of any particle in motion is equal to hc over, or what's the equation? H over mv. H over mv, and v is the velocity and m is the mass. H is Planck's constant. So what this means is that if I go and I take my bottom of page 3 where it says matter waves, that's page 2. Okay? No. The front is page 1, the back is page 2, then the front of the next page is page 3. Yeah. Page 5? Oh, bottom of page 5. Okay? I take my tennis serve and I hit a 100-mile-an-hour serve down the tee. Okay? So I'm here. That tennis ball actually has a wavelength, a wave characteristics to it. It has a wavelength and a frequency. Now, sure, I'm putting spin on it. It's curving just a little bit, but that's completely different than the wavelength that de Broglie says that it has. If I take the mass of the tennis ball in kilograms, the speed of the tennis ball, divided into Planck's constant 6.63 times 10 to the minus 34th, I can get the wavelength of that tennis ball going through the air. Now, it's going to come out on the order of 10 to the minus 29th, something incredibly tiny, immeasurable, insignificant, not noticeable. It's just, there's the wave nature of that serve of any macromolecule, big molecule, is going to be so insignificant, it's immeasurable, we can't detect it. However, you get down to the mass of an electron, traveling near the speed of light. Dividing that in, now the wavelength becomes very, very measurable, very quantifiable. And it turns out that the wavelength is about the diameter of the atom. So Schrodinger took that concept that the electron, that matter could have a wave characteristic to it, and he described the position and the energy of the electron in terms of its wave characteristics. And he said that it's in this complex standing wave pattern. Okay? Whoops. I'm smashing the rest of the spring. Okay? Matthew, come here. Come over here. I'm over here. Let's take this and walk against the wall over there. Okay? Yeah, just don't let go. Okay? So if I take this spring and I send an impulse down, you can see the wave going back and forth. You can see it go that way, and then you can see it transmitted back. It's bouncing back and forth off the two ends. Okay? So I'm sending that wave down. But if I continue to send the wave in a constant rhythm, now I can make what's called a standing wave pattern. Okay? So I have this standing wave pattern. And so right now there are two crests, and that area right in front of Victoria where there's basically no motion, is called a nodal region. Okay? A nodal, N-O-D-A-L, it's a node. It's an area of no displacement. Now, if I change the energy at which I'm transmitting, I can go, if I get it just right, there we go. Now I have 3 crests and 2 nodes. Notice once again that I had to get the rhythm just right, but I have a whole number of crests between me and Matthew. I can't make a partial number of crests. It has to be a whole number of crests in order for the standing wave to be able to be generated. Okay? Now if I change the energy again, increase the energy. Okay? Now we have 3 nodes, 4 wave cycles, 4 crests. Okay? I'm running out of gas. Okay? But as I change the energy, I can change the wavelength, but it always has to be a whole number of wavelengths. Okay? That's very important because, okay, good job. What Schrodinger said was that the electron, and Bohr said that the electron can only have certain fixed energies. Schrodinger explained that saying, well, it's in a standing wave pattern. Now, that was a 2-dimensional, just X and Y, up and down. He's talking about a 3-dimensional wave around a central nucleus with the electron going in all 3 dimensions. But he's saying still, the only way that standing wave pattern can form is if we're at certain distances from the nucleus. Still, and the distance is based upon the energy that the electron would have. So as a result, he was able to do the exact same explanation as Bohr, but treating the electron like a wave. So, according to Schrodinger, the electron had both a particle nature and a wave nature to it. And in turn, the reality is that there are, what are you guys just watching? You're fascinated by the fact that it moves? Okay? The electron actually gives, I'll stand back here. The electron actually has diffraction patterns. Diffraction is a wave characteristic. So they can actually have diffraction patterns formed from an electron, meaning that the electron has very distinct wave characteristics. Now, the unique thing, though, is have you ever heard of Schrodinger's cat experiment? I mean, it's kind of, they allude to it. Big Bang show is going to allude to Schrodinger's cat. I was actually just watching, it might have been the show Elementary, the Sherlock Holmes thing, and I think he might have said something about it, or there was some show I was just watching and they made just a random reference to the Schrodinger cat thing, and then he says, you won't understand, and moves on. But the Schrodinger's cat, now this, just for you pet lovers, this is a thought experiment. This was not actually performed. Okay? You get a box. You put a cat in a box. Okay? You put the cat in the box and you put a vial of poison in the box with the cat. And the vial of poison is connected to an electronic switch that's connected to a radioactive particle that has a 50-50 chance of decomposing, of emitting a radioactive alpha particle. Okay? Its half-life is such that it's a 50-50 chance. If it emits the radioactive particle, it sets off the trigger, breaks open the vial, the cat dies. If it doesn't decay, then the vial never breaks, the cat lives. It's in the box. You can't see inside the box. Schrodinger says that until you open the box and look at the cat can both be alive and dead at the same time. It can exist in both states. It's not until you go and look at it and try to observe it do you force it into the either alive or the dead state. Again, theoretical. Okay? It's existing, but hearing would be an observable thing. Until you do something to observe the cat, it can be in both alive and dead at the same time. By observing it, you're forcing it into one state or the other. Yeah, it's very similar to that. Okay? Or if you answer a question and your wife's not around to hear it, are you still wrong? And so, I might need to edit that off the video. All the girls said yes. I lost my train of thought. So, the electron, he said, is the same thing. It's both a wave and a particle, and it exists simultaneously as such in the atom. But when we go to observe it, we force it into one state or the other. We can observe the particle nature. We can measure the mass of an electron. We know the charge on the electron. We know its particle characteristics. We also know that there's diffraction patterns and there's wave characteristics. And so we can study the wave characteristics or we can study the particle characteristics, but you can't study them both at the same time. By observing the electron, you're forcing it into one state or the other. But it really exists simultaneously in nature in both states at once. Okay? That's kind of the craziness of the quantum theory. And the reality is they've actually been able to make an electron be in two places at the same time. Okay? Where you say it's impossible for matter to be in two places at the same time. So the different quantum states, they've been able to, I don't understand that, but I read an article that they said they did it. So, some of that, but I mean, when you talk about the math here that Heisenberg is talking about, it's super way up here. So what we have now is a kind of a combination of both of their ideas. We still use Schrodinger's equations. We still talk about the electron as a wavicle, as an electron and a wave kind of combined. Okay? A particle and a wave. But at the same time, we use the Heisenberg uncertainty principle, and we say, but we still can't know exactly where that electron is going to be at any given point. All we have is this probability. So rather than using Bohr and Rutherford's idea of an orbit around the nucleus, now we have what's called an orbital. And these areas around the nucleus where the electron might be based upon the high-level mathematics, are what we now know as our electron configurations. Okay? So I'm going to take a quantum jump, and what we're going to do is look at these electron configurations and try to relate it to the quantum numbers. Okay? So we know from last year, or from 2 years ago, Chemistry 1, that we have our arrow diagram. We have 1s, then we have 2s, then we have 2p, then we can have 3s, 3p, 4s, 3d, 4p, you guys remembering this? 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d. Okay? So this is our arrow diagram. This is what we say is the way the electron is arranged around the nucleus. This is Mr. Graeber's, famous soldier, please don't fire, the SPDF whole thing of all your orbitals. But all of this is really based upon Schrodinger's equation and the quantum numbers that are in the variables in that equation. So what I want to do is we want to relate how did we come up with this? How do the quantum numbers explain this, or how is this a model of the electron configuration? The quantum numbers are really the basis for this. Why do we only have one sublevel on the first energy level? Why is there only one orbital on that sublevel? Why do we have 3p orbitals? Why do we have 5d orbitals and 7 f's? Well, how did they come up with all of that? It's all based upon these quantum numbers. So if you go now, and I don't know what page it starts on in the notes, but where it talks about quantum numbers, I want to relate it to this. And it's all detailed very redundantly, actually, in those notes. I'm going to kind of go over it more quickly. But we have 4 quantum numbers. Okay? 4 quantum numbers. The first one is N, and it's known as the principal quantum number. Principal in this term means main quantum number. It states the energy level the electron is on. Okay? Now, it has to be a whole number, again because of Schrodinger's idea that the standing wave can only be a whole number of wavelengths, distance-wise from the nucleus. There's only certain distances that standing wave pattern can form. And each distance corresponds to an energy. These are all energy, quantized energy levels. So everything is based upon its energy. But the distance from the nucleus is related to its energy. So it's going to equal from 1 to 7, but it's going to be a counting number. In other words, no fractions. We don't have an energy level 1.5, 1.75. It's always 1, 2, 3, 4, 5, 6, 7. It's the main quantum number. So this is really my N value right here. N equals 1, N equals 2, N equals 3, N equals 4, N equals 5, 6, and 7. Now, again, the word quantum means fixed, fixed amount. So this is the quantum theory. The electron can only have fixed amounts of energy. It can't just have any amounts. So the energy level N is specifying, that's your main amount of energy, but then we can have sublevels. So your L is your second one, and that's known as your azimuthal quantum number. Now, I used to just think, that's just some guy that kind of came up with this, maybe did some studies, they named it after him and all that, until I got a satellite dish. And then my satellite dish wasn't working one time, and I went to see, and I went and checked the settings on it, and all of a sudden I saw this thing said azimuthal coordinates. I said, ooh, I've seen that word before. I thought it only dealt with electrons. So I actually looked it up. Now, this was actually before they had the internet. At least I was in Chelsea before the internet got to Chelsea. But 2 years ago. No, it was, I just moved, so it was about 15, 16 years ago. They actually did have the internet, but I don't think I had it at my house. I looked it up in an encyclopedia. That's the point I'm saying. An actual encyclopedia. And it talked about the azimuthal azimuthal coordinates as being a three-dimensional coordinate system. It's what satellites use in space so they can identify where they are in orbit around the Earth. Because you need the X, Y, and Z coordinates in order to locate something in a three-dimensional area. Okay? So the azimuthal quantum number is talking about what is the orientation, how is it arranged around the nucleus? Where is the electron going to be? So it's going to tell us that. And so it too is limited. It's based upon the value of N. Again, Schrodinger had to quantize the energy. So in order to make everything work and describe it, L can only equal from 0 up to N minus 1. From 0 up to N minus 1. So if N equals 1, what can L equal? 0 up to 1 minus 1, which is 0. Get your calculators out if you need to. Okay? Being sarcastic. Okay? So L can only equal 0. Thank you for at least responding. Some of y'all are just looking at me like, seriously? If N equals 2, what can L equal? L can equal 0 or 1. If N equals 3, L can equal 0, 1, 2. So, what do the values of L mean? Anytime L equals 0, that always corresponds to an S-type sublevel. L equals 1 corresponds to a P sublevel. L equals 2 is to a D, and L equals 3 to an F sublevel. So what does that mean? That means when on the first energy level, what's the only possible value of L? 0. So on the first energy level, what's the only type sublevel that's possible? An S. So we only have one S. On the first energy level, you only have an S-type sublevel. When n equals 2, L can equal 0 and 1. So on the second energy level, what type of sublevels can we have? S and P. So we have the 2S and the 2P. Okay? When n equals 3, L can equal 0, 1, 2. So on the third energy level, we have S, P, and D. So every time you go to another energy level, you have another sublevel. So we have the S, the P, the D, and the F. So there are two obvious questions that arise from that. Anybody want to guess one of them? What if n equals 7? Okay? There are theoretically, starting on the fifth energy level, another sublevel. But the letter stands, it's just going to go alphabetical after the F. It's going to be G, so you can have a 5G. On 6, you can have a 6G and a 6H. And on 7, you can have a 7G, 7H, and a 7I. Now what happens is that they're going to be way up in here, and if by the time an electron would have enough energy to get into those sublevels, they actually have so much energy that they can escape from the hold of the nucleus, and they become ions. So theoretically they're there, but in practicality they're never occupied because they would have too much energy to be held by the nucleus. They'd be too far away. Now, that's the first question. It's a good question. But if they go alphabetically, G, H, and I, why didn't they start A, B, C, D? So what's the second question? Why did they choose S, P, D, F? Okay? Shoot. Yeah. As creative as Mr. Graver's Soldier Please Don't Fire. By the way, I've never heard the story. I've only heard of the story. Okay? I asked him to come in and do it for the class. Last year's class wanted him to do an encore presentation of it, but he refused. Okay? Because apparently he does it to where you think it's a real story, and then, he kind of sets you up on that. Oh, I thought it was so real. I've heard some of my students say that. But when you look at these lines here, to us, they just look like pretty colors when we look at the atomic spectrum. When we look at the through the glasses and we see the hydrogen spectrum and all the different colors and we say, ooh, this is so cool, pretty. We just see just colors and lines. But a spectroscopist, okay, and that's not just an angry scientist, okay, that is somebody that studies the spectrum. Okay, thank you. I'm here all day. A spectroscopist. An angry scientist? Okay, come on. They lose something if you have to explain them. Okay? Pissed. He was pissed. A pissed. I know, he doesn't. He still doesn't get it. A spectroscopist? Anyway. Upset. And I'm supposed to teach. Help me, Lord. He's saying this. Hey, he's letting him know the soldier story wasn't real. Is that what he's saying? Okay. Yeah. I was expecting that to be something Rizwan would ask. All right. Anyway, when a spectroscopist studies these lines, there's actually 4 different types of lines. They can tell the difference when an electron transitions from an S or a P or a D or an F orbital. So they name them S for sharp, P for principal, D for diffuse, and F for fundamental. They just kind of describe the different types of lines that were formed when the electron transitioned. So that's where the SPDF, it's not just random letters, it's when they were studying the spectra of the atoms, they had the S sharp, P principal, D diffuse, F fundamental. You'll never have to know that, but it's just, but at the same, erase. I don't want to even study something that I don't have to know. I don't even want it on the paper. Okay? The point is that they're not just random letters. There's a reason for it. No, it's just alphabetical because they're never used. There's no lines ever to be given, so they can't describe a line that is not seen. So they just went alphabetical. Okay? So they don't represent anything. All right? So we have our sub-levels then on each energy level based upon the L value. Now, each sub-level has a certain shape. Now, remember we talked about in Schrodinger's equation that psi, that Greek letter that stands for the wave function. Now, that wave function to us has no real physical meaning. It's just a very complex. Now, to the mathematician that understands all that, that's fine and dandy. But for us, I just turned this off. For us, what's important is when you do psi squared, you square the wave function. And again, I don't understand the math on this. I'm just trusting that smarter people than me have validated it that it's true. Okay? Now, to be honest with you, according to Mr. Graber, and I haven't had a chance to follow up with the research, he says that there's a guy now that's doing more research on all this quantum mechanical stuff, and he's coming back to the idea that maybe Einstein was correct, that there's a concrete model of the atom, that it's not just all mathematical and theoretical and probabilities. Okay? So we're still trying to figure out, is it really true or not? Okay? It could all be bogus. But it's the best we got for right now, and that's what science does. Okay? I mean, just on a side note, I was just reading an article. I get a futurism little blurb on the email, and it's talked about maybe they figured out what dark matter is made out of. And they go into this whole theoretical thing of these things called axions and trying to figure out why there's 25% of the mass of the universe is unaccounted for. Where is that mass? But again, they're making up these theories of what could be out there, what's happening. Well, when light was trying to be understood, okay, when we were trying to figure out light, they said, well, it's a wave, it needs a medium. So they said, well, there must be an ether out in space. There must be this invisible medium in the vacuum that's called an ether that the wave travels on. That was their theory for a long time, because waves need a medium. There must be a medium. So that's kind of what I think they're doing in dark matter. They're just kind of making something up. We need something out there. These axions that are super tiny, that, they're occupying that space. Yeah, so that's what light, now we say. That was the theory beforehand. But then when they came up with electromagnetic radiation, it kind of disproved that one, and it makes its own medium. So, when we look at these, when we do psi squared and we want to know what the shape of an orbital is going to be, each one of these dots represents a possible solution. This is a 2p, this represents the 2p orbital. Okay? So we say a p orbital is this dumbbell shape. Well, how do we come up with that? When you take Schrodinger's equations, take the psi and square the wave function, you don't just get one answer. You get a bazillion answers. And when you plot that on a three-dimensional graph, each dot represents the possibility of where one electron might be. If it had 2p, that means it's going to be n equals 2, L is going to equal 1. If you plug that in and solve for it and get the wave function and square it, these are all the possible places where the electron might be. Obviously, where it's darkest, it's the most dense, that's the highest probability of finding the electron in this area here. But yet there's still possibilities of the electrons being way out here. So our minds need a shape. It needs something concrete. So we design a shape and we say, well, it's going to be this shape. We just draw the boundary where there's a 90% probability of finding the electron at any point in that space. Doesn't mean it's confined to that space. It just means that's the greatest probability. This is the Heisenberg uncertainty principle. We don't know exactly where the electron is. We just can give a probability saying that if it's got this much energy, most likely it's going to be in this space. The highest probability. So instead of an orbit, we call this an orbital. And it's all based upon probability. So when we say the shape of an S and we plot an S orbital and we do all the dots for an S orbital, it's going to look like this. So n equals 1, L equals 0. The electrons, there's a 90% chance the electrons are going to be somewhere in this shape. A 2s is going to look like this. It's going to still be spherically shaped. It's just going to be bigger. Now this is where we do like a Russian doll. Okay? This goes on the inside of this. You know those Russian dolls, you open it up, the smaller one's exactly like it, and you open it up, there's another smaller one just like it. So this is inside of this one, and so the nucleus is in the center of this one. So you have a sphere, and then you have another sphere that's circling it, bigger, but then there's this nodal region, an area of no or low probability of finding an electron. Then remember the node in front of Victoria, there was zero motion. So this is a nodal region. So a 3s is going to be, here's your 1s, here's your 2s, here's your 3s, and there's these areas in between, these nodal regions, where there's a low probability of finding electrons. 1s, first energy level, second energy level, third, with a gap in between. Yes, sir?
So would it just be on the white lines, or would it be around the white lines?
No, it's the colored areas is where the electron's going to be. The areas, the white areas, are where there's no electrons.
But in order to get from one sublevel to another, you
Okay, now that's where Bohr comes back to these quantum jumps. We have no idea when it transitions, when we talk about going from 3 to 2, we have no idea how it gets from 3 to 2. Okay? It just does. And when it does so, it releases energy and it's just there. I know it's crazy. It just does. And that was the whole crazy thing. And that's what Einstein just refused to agree to. He said it can't be just that. We've got to have a better model. There's got to be something. This can't be a matrices of numbers and just this, this probability thing. This is matter. This is solid. There has to be something concrete. We have to have a physical model of the atom. And we haven't been able to wrap our brain around where the electron is and get a true physical model. Right now, it's a series of mathematical equations that describe the electron. So, this new guy is trying to come up with a physical model. But the whole idea is that all the shapes of these orbitals are designed based upon that wave function squared, plotting it. Where could the electron where might it be? What's the probability? And we draw the shape just to say there's a 90% probability. So when we do that, anytime L equals 0 and we have an s orbital, it's always going to be spherical. The only difference is that a 2s is bigger than a 1s. A 3s is bigger than a 2s. So this one encompasses this one, which encompasses that one. Russian dolls. And there's always just a gap in between where there are no electrons. So we're describing where the electron is going to be based on its energy. Now, when L equals 1, we have a p orbital. Our next quantum number, I'm about done where we can take a break. Our next quantum number is m sub L. And because it's sub L, that means it's related to L. M sub L is equal to the magnetic quantum number. It equals minus L up to plus L. Minus L to plus L. So M, the value of M is based upon what value of L you have. So if L equals 0, M sub L can equal minus 0 to plus 0, so what's the only answer? 0. Now, the 0 isn't important, but how many answers are there? How many possible answers are there for m sub L when L equals 0? 1. 0 is the only possible answer. Because it can equal, m sub L can only equal minus L to plus L. So if L equals 0, m sub L can only equal 0. Only one answer. So whenever we have an S sublevel, how many orbitals are there? Just one. Just only one way, one orientation in space for a sphere. You can't orient it any other way in space. It's always a sphere. Just one answer, one orbital, one line. Okay? But if L equals 1, which is a P sublevel, what can M sub L equal? -1, 0, and 1. How many answers are there? 3. Each one corresponds to a different orbital, which simply means these are degenerate orbitals, meaning equal energy orbitals, but they're different orientation in space. So what we have is -1 is going to be directional. It's going to be a px. It's going to be the p orbital on the x-axis. Or if we put in n equals 2, L equals 1, m sub L equals 0, then it's going to be on the, say, z-axis. Or if we put in n equals 2, L equals 1, m sub L equals plus 1, then it could be on the y-axis. Same shape, same energy, just different orientation in space. 3 different ways we can orient this one in space. X, Y, and Z axis. So that's why we always draw 3 lines for the P sublevel. Then, if L equals 2, M sub L can equal and how many answers is that? 5. So we have our 5 d orbitals. We always draw 5 lines. Now that just represents, again, 5 different orientations in space, which they're all kind of messed up. But here's one. Let's see what we can do here. There's 1. There's 2. Here's 3. Here's 4. Notice that these would fit right in between here in this empty spaces, kind of like this. Okay? Yep, it goes like that. And then finally, the 5th one is kind of this weird dumbbell shape. Okay? Each one of these is one orbital. This is just a little yeah, it is, it's flashing. Okay? So this is just kind of you guys are so easily amused at seeing yourself. Okay? Now, so again, if we look at the electron density map for this, when you plot psi squared, you get, this is how we get the shape. So this is our xy on the xy axis. This is the x squared minus y squared. So these are just your different orientations of space, each one of these. So we have the plot of the wave function squared, our probability of where the electron might be. So we plot it all, so then we draw the shape based upon a 90% probability that's going to be there. So we get our 5 d orbitals that all kind of look like this. This is this one right here. Okay, it's kind of got that donut hole kind of in the middle of it. No. Usually what we do is we call this rose petal. Yes, sir.
What do you get off each orbital, like spins?
Well, you get 2 electrons can go into any orbital. That's going to be our last quantum number. And they have to have opposite spins. Yeah, it's a plus and a minus. It's an up and a down. Okay? Now, so if if L equals 2, L equals 0 is an S, L equals 1 is a P, L equals 2 is a D. If L equals 3, it's what type of sublevel? F. So if L equals 3, what can M sub L equal? -3 to 3, which is how many answers? 7. So there are going to be 7 F orbitals. Now F orbitals are crazy complex. This is what your 7 F orbitals are going to look like. Each one of these is a single orbital. That's one orbital, that's one, that's one. This is one orbital. It's got 8 lobes on it, but it's one orbital. One orbital, one orbital, one orbital. Okay?
So there's so many places that electrons how do you determine what they exactly?
You just know that it's going to be in this general vicinity.
And only one.
It's only 2 electrons can go in this one, only 2 can go in here, 2 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 in here. That's the most probable place, again, based upon that electron density map, the plot of the psi squared, that wave function squared in Schrodinger's complex math equations.
So that's where like any 2 could be.
Any 2 could be anywhere in here. Now, how are they moving in there? We don't know. Heisenberg uncertainty principle says we don't know. How does it go from here to some other sublevel? We don't know. It just does, just like the guy just kind of moved from floor to floor. Okay? Our brains can't wrap around it. It's okay that that doesn't make any sense. It doesn't make any sense to me either. I just accept it. Okay? But just like Niels Bohr himself said, if you feel like you understand quantum mechanics, you just haven't thought about it enough. Because nobody can really understand it because it doesn't make sense. It doesn't obey natural laws.
What kind of math would you have to take in order,
Calculus 20. I mean, you just have to be a total math geek. I mean, you just have to just know the math. And I only had 2 semesters of calculus, so I'm trusting a lot.
How do you determine the form? What did Schrodinger do?
Wait,
I don't know.
Finding those locations.
Maybe he's doing drugs, and if something came to him, I mean, maybe the girlfriend was exceptional. I don't know. Just. Okay. Well, we need to know this because all bonding, the entire periodic table, our entire electron configuration is all based upon what we have here. 1S, soldier, please don't fire, the SPDFs, and all of that, which is where we're kind of going right now. So, our last quantum number is m sub s. And it's just plus 1/2 or minus 1/2. Now the value 1/2 means nothing. It's the fact that it's plus or minus. Okay? And all that means, and this is called the Pauli exclusion principle, is that in any given orbital, you can only put 2 electrons, and they have to have opposite spins. Now when a charged particle radiates, it generates a magnetic field. Both of these electrons are negative. They're both going to repel each other. But because they have opposite spins, then they generate opposite magnetic fields, and so as a result, they can occupy the same space. But there's only 2 possible spins, plus and minus. So only 2 electrons can occupy the same space. That's the only way they can kind of negate the electron-electron repulsions that they have.
When you say spin, are you talking about?
Well, up until 2 years ago, I thought they actually were spinning on their axis like the Earth. Okay, because it talks about the spin. But I read an article 2 years ago that said, no, I got to quit reading, that they're really not spinning on their axis. They just have a kind of a charge. Now, how does the spin change? How does that charge change? I don't know. To me, it's a lot easier, and I would recommend you just think of it as spinning on the axis, that one's counterclockwise and one's clockwise, and as they spin, they generate a magnetic field. That's how my brain deals with it. If you want to get more theoretical, somehow it just does it. Okay? But to change spins, all you have to do is flip over on the axis. because then you go in the other direction, then your spin changes, and that's how electrons can go from one orbital to the next. When they need to change spins, they don't have to go back the other way. You just flip over on the axis. It basically has the opposite spin. So that's the way I perceive it, as spinning on its axis. Although theoretically, according to the article, it doesn't really spin. I don't know what it does. Okay? Again, nuclear physicists, I mean, you got your high level science to be able to understand the quantum mechanical model, really understand it. So we're just trying to get to the end result. So the Pauli exclusion principle says we can only have 2 electrons in any orbital, and they have to have opposite spins. So now we have, based upon the quantum mechanical model, based on Schrodinger's equations, we now have this model that we draw to try to represent what the electron cloud looks like. Okay? So if I have, this would be an electron configuration of helium. Now lithium has how many electrons? 3. So where would the third one go? Into the 2s. Beryllium has how many electrons? 4. So where's the next one going to go? 2s, but down. Then boron has 5. So it's going to go here. And then what about carbon? Would it go here? You remember that you put 1 electron into each orbital before you begin pairing them up? And they all have to have the same spin. That's Hund's rule. And that's given on one of the last pages. So we go, that's nitrogen. And then we go back to oxygen, fluorine, to neon. So then after 10, we go to 11. Sodium would go back into the 3s. And then magnesium. And then you jump across on the periodic table and you go to aluminum, to silicon, to phosphorus. Okay? And then to sulfur and chlorine and argon. And then when you get past argon, 18, where's the next electron go? For this is where we get the overlap. Okay? And we'll talk about the overlap tomorrow, but there is an overlap. Why there's an overlap? So with 4s, so that would be potassium, 19, and then calcium, 20. Now notice on the periodic table for the first time, when you go to 20, you don't jump across that center section. Because what sublevel's next after 4s? The 3D. So then you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now you have 30 electrons, and that's zinc. And notice you're at the end of that center section. So what comes after 3D? 4p. Okay? So then you're 31, which is gallium. Okay? And then so on and so forth. You just keep filling all the way up. So, let's look at the code then. What a corollary to the Pauli exclusion principle, says that no 2 of these electrons can have the same set of 4 quantum numbers. So we have, this is gallium, 31 electrons. I want to know, well, what would be the 4 quantum numbers for that electron? There's 31 choices. I'm just randomly, 1 out of 31. I'm just picking this 1 electron. What are the 4 quantum numbers going to be? N, L, M sub L, M sub S. What are those 4 quantum numbers going to be? N is 4. Why is N is 4? Somebody else tell me. It's 4th energy level. Okay, how do I know it's on the 4th energy level? Because it says that 4 right there. Okay, so N equals 4. Now, when N equals 4, what are my possible values of L? What can L equal when N equals 4? 0, 1, 2, and 3. What does that mean? What does each of those represent? On the 4th energy level, I can have, what type of sublevel is this? S, P, D, and F. So when N equals 4, there are 4 possible sublevels. S, P, D, and F. Which sublevel is the electron that I'm interested in? It's in the P. So that corresponds to L equals 1. So of these 4 values, I'm going to pick L equals 1 because it's in the P sublevel. All right? So L equals 1. Now when L equals 1, what can M sub L equal? Minus 1, 0, and 1. So we say minus 1, 0, and 1. So which one is our electron in? The minus 1. And then it can have the possibilities for spin are only plus 1/2 or minus 1/2. So this one's going up, so we just say plus 1/2. Now it could just as easily be going down. Just as easily be going down. So if I just randomly pick another electron, let's pick this one right there. So this is electron 1, this will be electron 2. Which sublevel is this one in? 2. Okay? So what's N going to equal? So what are my possible values of L when N equals 2? 0 and 1. Our electron's in which one? The 0, because it's the S. S always corresponds to L equals 0, or L equals 0 always corresponds to S. L equals 1 always corresponds to a P. L equals 2 a D. L equals 3 an F, always. So this is in the L equals 0, and then when L equals 0, what's the only possibility for M sub L? 0. And since this one's going down, we're going to say minus 1/2. This is our quantum code. It's our own Da Vinci code. The quantum code. So if we went the other way, and I said, okay, well, what is it going to be if it's 3, 1, minus 1, minus 1/2? What electron is that? Okay, so somebody else tell me if he's right or not and why. Okay, I'm seeing some head nods. Okay, front row, somebody tell me which one? N equals 3 tells me it's which sublevel? I mean, which energy level? 3. So I know it's one of this one, or these. Okay, it's got to be N equals 3. So that's the first thing tells me, okay, so now I've narrowed it down to one of these. So then L equals 1 tells me which sublevel. The P. So now I've narrowed it down to these 6. No, because L, that would be M sub L value. The L equals 1 always corresponds to a P. If it was the D, L is going to equal 2. Okay? So now we go negative 1, 0, 1. So the negative 1 means now I've narrowed it down to that sublevel. This orbital on that sublevel. And since it's minus 1/2, it's the down arrow, so it's going to be that one. Okay? So what would that one be? Okay? 3, 2, negative 2, negative 1/2. And I really meant to pick this one because that would be 3, 2, negative 1, negative 1/2. So again, the difference between this is this number. That was to try to answer your question. They have the same M sub L value, but different L values. Okay? That's not okay? I'm seeing a pained look. Are we getting it? So, any atom, we're going to use the same model for all atoms. And we're going to, tomorrow or the next day, we'll talk about how we differentiate that. Okay? But for now, we're going to use the same model for all atoms. So this is called an arrow diagram. But it takes up a lot of space. So if we want to write an electron configuration, Yeah, everybody's going to go back and watch the video. Friday night fun. Yeah. Hey, Mom. It's all written down. I already wrote it all down for you. I don't know if I can do this backwards. Yes. I said, yeah. Okay. So, let's do this. I want to do an electron configuration. Let's just pick an element. It's bigger. Okay? Gold. Well, okay, I like rubidium. Let's do rubidium. Okay? 37. It's just the reason why I don't want to do silver or gold is because they actually have a little bit of irregular electron configurations. Okay, so I don't want to get into that discussion. So rubidium is element number 37. So how many electrons is it going to have? 37. So we're just going to start at the bottom, and that's known as the Aufbau principle, and it's written there near the end of the notes. You always start and fill the lowest, and you only put 2 electrons. The Pauli exclusion principle, only 2 go into any orbital, and they have to have opposite spins. Then you go up to the next one, and then Hund's rule says we put 1 electron into each before we begin pairing up. Now that's 10, 12, 18, 20, 30, 36. We're going to 37. So how many more do we need, obviously? 1 more. So it's going to go into the 5s. So that's the arrow diagram. Now, some teachers teach this going down instead of up. That's 100% fine. Some teachers teach it going horizontally. There's all different ways of representing this as long as you have 1s, 3ps, 5ds, 7fs. Now,